In this reaction, we're going to look at the reaction of carbonyl compounds with amines. In this case, we're looking at a ketone in cyclopentanone with a primary amine. This is a primary amine because that nitrogen has two NH bonds. And in this case, we are expecting an imine to form in which the oxygen in that cyclopentanone is replaced by the nitrogen in our amine to form this compound, in which the cyclopentane in the cyclopentanone is present here, and the isopropyl group from the amine is present still attached to nitrogen. While this reaction will take place under neutral conditions, it's much faster if it's acid catalyzed. And so we're going to show this mechanism with an acid catalyst here. And in the first step, the ketone is electrophilic, but it's not as electrophilic as it could be. And so the first step is to protonate the ketone, which is going to create a much better electrophile. Because now our oxygen has a positive charge. And so that carbon on the ketone is much more electrophilic because it has this resonance structure. Where the positive charge is on the carbonyl carbon. In a second step, then the nucleophilic nitrogen is going to come in and attack the carbonyl carbon and kick those electrons up to form a tetrahedral intermediate, in which we have an alcohol or an OH group and a nitrogen with a positive charge. The next two steps are a proton transfer, in which we have to we're going to use a generic base to remove a proton from nitrogen. In this particular reaction, the best base around at this point is probably another one of these amine compounds, but it could be something else that's removing this proton. And so initially that produces the neutral intermediate, where we have a neutral oxygen and a neutral nitrogen in this amine. And that recently generated acid, where we had produced this generic base that's been protonated, is now going to protonate the alcohol. So I'm going to take the oxygen and grab that proton. To generate this intermediate, in which now we have created a good leaving group in this protonated alcohol. And so the electrons on nitrogen, which still has a hydrogen on it, which I haven't drawn, the electrons on nitrogen can now kick down to form a carbon-nitrogen double bond and kick off that water leaving group to form this intermediate. And in a final step, we're going to use a generic base again to deprotonate this nitrogen. This now has a positive charge. and generate the expected amine as our final product. It should be noted that every step in this reaction mechanism is an equilibrium, but as a general rule, the equilibrium favors the products or the formation of the amine, um, and that some acid catalyzes this reaction. But if you add too much acid, it ends up shutting it down because all of the amine gets protonated and becomes less nucleophilic. The ideal pH of this reaction is about 1.5 pKa units or 1.5 pH units below the pKa of the protonated amine. As we said in the previous reaction, amines or the formation of amines is an equilibrium. And so you can undo the formation of an amine in what's called the hydrolysis of this amine. And in this case, the expected products then are the starting materials of the previous reaction, or cyclopentanone plus isopropylamine. And there are two ways that we can sort of force this reaction to completion so that it's not really an equilibrium. The first of which is to just use a lot of water. That's Le Chatelier's principle that's going to force this reaction towards the products by including a lot of reaction. And the second way is to use a stoichiometric amount of acid. So if you use a stoichiometric amount of acid, forces this reaction to completion. So under catalytic conditions, where we have a catalytic amount of acid, the amine is favored. Amine favored under catalytic acid. But the amine plus ketone is favored under stoichiometric acid. If you react an aldehyde or ketone with a secondary amine, rather than an imine, you obtain an enamine. So this reaction produces an enamine in which the nitrogen replaces the oxygen, but rather than a nitrogen-oxygen double bond, we end up with a carbon-carbon double bond. And so this cyclopentane from cyclopentanone winds up here, and the carbon-carbon double bond is in that cyclopentane ring. And the cyclic amine winds up on top here, where the oxygen was previously. So again, this reaction will take place very slowly without acid, but the acid catalyst makes this much, much faster. And so in the first step, what we expect to see is the protonation of the ketone to make the ketone more electrophilic, just like we saw with the imine formation. So that protonated ketone is far more electrophilic. In the last reaction, we saw that resonance structure that showed why it's more electrophilic. I'm going to skip drawing that this time and just attack this resonance structure directly with the nucleophilic nitrogen, and that's going to kick up those electrons on oxygen to produce a tetrahedral intermediate with cyclic amine here, this protonated. In the last reaction, we saw a proton transfer that occurred in two steps, where a base came in and removed this proton, and then that newly protonated base protonated the alcohol. In reality, that certainly is the more likely scenario as to what's happening. But in this example, I'm going to show it in one step where this alcohol directly deprotonates this amine to give you this product here. And just like last time, the electrons on the amine can kick down and kick off water to form this nitrogen with a positive charge. Unlike last time, because we started with a secondary amine, there is no proton on this nitrogen to deprotonate. So rather than protonating or deprotonating that nitrogen, which we don't have, we're going to deprotonate a carbon in a elimination type reaction, where now we're looking at the alpha carbon. So this carbon was the carbonyl carbon, and the carbon right next to it is known as the alpha carbon. And we're going to deprotonate that with some exogenous base. We're just going to use a generic base that's going to come in and grab that proton. That's going to kick these electrons down, which is going to kick that pair of electrons up to produce this enamine as the final product. Again, under each step in this reaction is an equilibrium, although that last one I showed a little wonky. This is a reversible reaction. Each step in here is an equilibrium, but under normal catalytic conditions, the enamine tends to be favored. And if you want to force it towards the products, you could run this reaction in the presence of excess amine, which is going to push this reaction towards the products. Like amines, the synthesis of enamines is a reversible reaction, and so we can undo it through hydrolysis. In this example, we're going to undo the reaction we just did, and so the hydrolysis products of this enamine are cyclopentanone and this secondary amine. Like enamines as well, Under catalytic conditions, so with catalytic acid, the equilibrium generally favors the enamine. But under stoichiometric acid, so that's one whole equivalent of HCl, the hydrolysis product or the ketone and the amine are favored. The hydrolysis, like the enamine or like the amines, is the microscopic reverse of the formation. And so if you know the forward mechanism, you know the reverse mechanism. Now that we've seen how amines react with carbonyls to form amines, I want to take a look at a couple of examples of how these amines can be used in chemical synthesis. The first example I want to look at is the Wolff-Kishner reduction. And we've actually seen this reaction before in class when we talked about the modification of groups hanging off of benzene, but we didn't know how the reaction worked. But now that we understand how amines form, we can take a look at how these compounds react, or the mechanism of these compounds. And before we did this mechanism under acidic conditions, but now the Wolff-Kishner reduction is under basic conditions. And so we're going to take a look at how this mechanism might take place under basic conditions. So we can't protonate the carbonyl to make it more electrophilic under basic conditions, and so we're just forced to have to attack the carbonyl directly. And I'm going to abbreviate my phenyl ring with a pH. We get a negative charge on an oxygen, and a positively charged nitrogen. And then we're going to have to do a proton transfer to remove the proton on nitrogen and protonate this negative oxygen. That likely happens in 2 steps, but I'm going to show it as an intramolecular proton transfer to speed up a bit, because this is a long mechanism. So we get to this neutral tetrahedral intermediate, and ordinarily I would say that this compound does not have a good leaving group, but because we're under strong basic conditions, it's reasonable to kick off an O-. And so I'm going to have these electrons on nitrogen kick down and kick off that hydroxide. That's going to form this compound, which will rapidly be deprotonated, probably with the hydroxide that we just formed. To form the amine. Now, because we're under strong basic conditions, we're going to deprotonate again. I'm going to get another hydroxide. Remember, we started with hydroxide in this reaction, and so this hydroxide is likely one of these that we started with. And we're going to deprotonate the most acidic proton in this reaction, which is likely, it's not likely, it is this NH proton. And that's going to give us this negatively charged intermediate. And nitrogens with negative charges are quite basic, but this one is resonance stabilized. So we're going to draw this resonance structure. Get rid of that stray mark there. It looks like this. And that negatively charged carbon is rapidly going to pick up a proton, likely from the water I just formed, to form this compound here. And then OH minus is going to come in and deprotonate that nitrogen in the end. And that's going to kick the electrons here to form a nitrogen-nitrogen triple bond, which is going to kick these electrons down to carbon to form another carbanion plus N2 gas. And that carbanion is rapidly, again, going to pick up a proton from the water I just formed to give the final product, which is just this compound here. And you can see that's just our starting material where we have cut off the carbonyl and replaced it with two hydrogens. So we've seen this in the context of benzylic ketones, and it's much easier with benzylic ketones because of this resonance stabilization in this carbanion. However, with heat, you can do a Wolff-Kishner reduction on non-benzylic ketones. The second type of reaction I want to look at where amines are used in chemical synthesis is something known as reductive amination. And this is really a series of reactions and is a great way to make secondary amines. This is a great way to make secondary amines. And so if you take an aldehyde or a ketone and react it with a primary amine in the presence of an acid catalyst, we have seen that that makes a imine. And so if we take these two things together, I'm going to sort of chop this oxygen off and stick this nitrogen where it was. And so that's going to form this compound here. And that's the end of step one of this reductive amination synthesis. And in step two, we're going to treat this imine with sodium borohydride. And we've seen sodium borohydride as a reducing agent for carbonyls, but it will also reduce imines. And so if we draw out borohydride, these electrons in this boron-hydrogen bond can attack the imine carbon and kick some electrons up to that nitrogen, and that's going to form this compound with a negatively charged nitrogen, and then in a final step, H3O plus is used to protonate that nitrogen and produce the desired secondary amine as the final product. And so if we're looking at this, we can see that this portion of the amine came from the ketone, and this portion of the amine came from the starting primary amine. That's going to wrap up our video on the reactions of amines with aldehydes and ketones.